Okay, so just 1 second. I would like to see if you can. Can you see me with through the webcam? I just would like to check if you can see my face. I think to see my face you should pinpoint me. Okay, very good. Okay, okay, perfect. I I just wanted to check because I tell you, yesterday during we have several meetings with directors these days, and yesterday during the meeting with the rector, he just summarized a little bit the results the results from the survey of students' opinion, the last one, and and basically he said that they got from Friday to Sunday some 3,000 responses from you, from all the students of Univo, and basically the response was fine. So thank you very much. Of course, not only to you, but all of your colleagues. But he said that several students pointed out that they can't see the face of the professor, and therefore they were a little bit, how to say, disappointed because they thought that having the opportunity to look at the face, it's something that gives us the feeling of being more connected. So I wanted to make sure that you can see me at least for now. So first, I have the chat in front of me. So as usual, if you have any question, let me know, and also please let me know if the connection gets difficult because I am using several devices. I am using the hotspot of the mobile, so it is a bit stressed, this connection, but I am checking with the mobile that you can see almost everything. And but in any case, if you have any problem as usual, just let me know on the chat. And don't be afraid also to step in with the micro. This is something that I want to stimulate a little bit more, so I can hear your voice, because I have the same feeling with respect to you. Sometimes, you know, I don't feel like there is a human contact with the students because I can't see you, and I'm not saying that you should turn on the video because this is not a good idea. At least not now, at least not during the lectures. Maybe that sometime we can try to organize um, a video connection, but not now. And but you can use the micro. So if you have any question, also feel free to use the micro. It is, I mean, it gives the feeling of a better interaction. Okay, let me now go back by sharing the screen. Okay, here we are. By sharing the screen, I go back to, let's wait that you can see it, but okay, good. I go back to the page of our course. First of all, as you have seen in the morning, there were some problems, unfortunately, because you know the problems always come in group, not alone. The problem is that just when the virus started, my server on which the website is running got a failure in one of the disks. And it's not a problem because it's backed continuously, but the problem is that sometimes during the internal check, the server gets stuck because he recognizes the disk failure and keeps reporting and refuses connections. So I need to get into the server in this condition and reset it. So I had to do it this morning, of course, as soon as I try to have access. But you have the alternative address. So if you experience any problem, you have the other server, the mirror. And you know, this problem will persist for a while because I am not sure when I'll be able to go into the office. But anyway, now it's working. So let's get again to the page of deductive methods for assessing water resources availability. First of all, I just wanted to tell you that the pace of our lectures is fine. We are not late. And as far as we are now, I mean, after, I don't remember the number of hours, but I checked that we did, but I checked with the calendar and that's fine. So we are, as I said, perfectly in pace. And so I also would like, when I have a clearer vision of our future in terms of schedule, I also would like to make plans for the exams. I already told you something like I want to wait for June for the exams, but I want to fix the dates well in advance, but we will have time to discuss this. Okay, so let's go to iMod. And first of all, let me point out some changes that I did to the web page. I think you already had a look at it. Perhaps the most important is the fact that I included these graphs, and I'll comment on them later, but I just want to point out the R code, which I embedded here. And also I wanna, probably I'll put it into a box in the future. The R code, I am highlighting it. I highlighted it with the mouse. I think it is interesting for the graphic parameters. The code is very simple. It's just a code to draw a graph, but what I did here in these figures is to use subscripts in C star is a subscript. And look at how the subscript was introduced, and the instruction is here. I'm not commenting now, just have a look at it. And keep it in mind when you will have to include subscripts in your axis labels, etc. Also, another interesting thing is the graphic title, because here I put first a Greek letter, which is, I mean, it's not that easy. Second, the value of the parameter was not manually introduced. So beta equal 1 in the first graph. 1 was not manually introduced. 1 is a variable in R, which is called beta k in this code. So it is not really easy to find out in the web how to write this instruction which I'm selecting. Main is the argument of the plot function that allows you to specify the plot title. And usually what the people do there is to write main equal between commas some text. Here the instruction is different because I had to use a bquote, which is bquote the R function that allows to combine values of variables with text. And again, we are not now discussing it in detail. What I suggest you, besides trying to learn in details what each R function does, this would be a bit difficult because you will learn several functions. You will have several needs when drawing graphs, for instance, and it's a bit difficult to learn everything, to learn and keep in memory everything that you will know during this course related to R functions. So I'm not suggesting you to look at the manual of bquote, at the help of bquote, and learn everything. What I suggest you is just to keep in mind what we did here. And we did two new things. Use subscripts and use variables in combination with text for writing text in the graph. Just remember that. So in the future, when you will have this need, you will remember that in this web page, you will find an example of the code. And this will save you some time, because otherwise, if you go on the web, these are high level instructions, high-level information, and it's not so easy to find help on the web, or it's not so easy to select what is the type of information that you need. So just keep in mind, and I think it is just enough. We are engineers, we need to be very practical, and to be practical, just fix in your mind that we did this here, and this is an example code. Of course, there are other solutions to do the same thing. This is just one. At the same time, I want to tell you that to draw the plots in R, the plot function, which I used here, I am now selecting it with the mouse, it's not the only solution. This is the basic plot instruction in R. There are other functions that can be used to draw plots. We already learned matplot. We already used it, but there are other functions available, and which I'm not now entering into any detail. Maybe that we will have some time in the future. Now, I want to make sure, also because I was not completely happy of my lecturing last time in terms of clarity, I want to make sure that you got the concept of this model. And again, I go up and let's see this relationship. The model has a basic relationship that's probability distribution. Okay, we learned what probability is, and it gives again a probability depending on essentially two parameters, Cmax and beta k. Cmax and beta k in this function are two parameters, namely two values that I can specify to give to the function a given shape. And of course, the shape of this function will be determined based on the catchment of my application. Just keep in mind two parameters. It's a probability distribution with two parameters. And it gives the probability that for a given point in the catchment, we have a soil water storage C star, which is lower or equal than it gives you the probability that we have a soil water storage in the catchment at a given location that is lower or equal than a given value C star. So again, I fix a value C star of soil water storage, and the function gives the probability that in any location I have less or has such water storage. Okay, and let's now just focus a little bit more in what is the meaning of beta tending to 0. First of all, let's see here, beta equal 1 means that you have a linear relationship between C star and the probability F C star. Perfect. Beta greater than 1 means that the convexity the function is concave, and the beta, so the convexity is towards the bottom of the figure. Beta less than 1, the function is convex, meaning that the convexity is upward towards the upper part of the figure. Now, what happens if, again, I want to stress this, what happens if beta is tending to 0? So it means that, for instance, if you take a C star, which is 99 in this case, you have a probability of 0 that in the catchment you have less storage than that, which means that everywhere in the catchment you have a very high storage, which is Cmax. Okay. Conversely, if beta increases, beta equal 100, means that even for a very small storage, you have a very high probability that everywhere in the catchment you have less storage than that. So even if I get a storage of 2, I have a high probability that everywhere in the catchment, the water storage capacity is lower than 2, which means that the catchment is impervious. Okay? So it's clear that if I go up and look at a generic shape of this function, the shape will change depending on the catchment. If the catchment is very permeable everywhere, I expect a convexity which is directed upward, beta less than 1. If the catchment is more or less impervious, I expect a convexity that is directed downward, beta greater than 1. Perfect. And the other thing, which I hope you understood, is this figure. So, as time passes during a rainfall event, you get at each time step a rainfall P. So let's suppose you have an event of 10 hours. Each hour you have PT, which is rainfall at each hour. The cumulative rainfall, under the assumption that we don't have any losses, we assume that it's equal to CT. And remember that CT is the water storage in the parts of the catchments that are not saturated, which is equal to rainfall, because if it rains over a very permeable catchment, you get that all the rainfall infiltrates, so all the rainfall is equal to storage. And then this shaded gray, dark gray area, we said under the curve, it's individual contribution to runoff, because the difference CT plus DT minus CT is rainfall at each time step. And if you multiply rainfall times the difference FCT plus DT minus FCT, or let me say, if you multiply rainfall times FC, whatever it is, you get rainfall multiplied by the fraction of areas that are already, that have a storage that is less than the considered storage at time t, which means runoff, because what rains over the areas that have less storage than rainfall, it's completely transformed in runoff, because it is rain that falls over an already saturated catchment. Because if the storage is less than rainfall, means that the catchment is saturated. So if I compute the integral under the red curve, I get from time 0 to time C max, I get the area under the red curve. The integral is the area under the red curve, which means contribution to runoff. And then the complement to 1 of this area is contribution to storage. So let's assume that I hope this is clear. And if not, just 1 second, I get the chat, which disappeared. Okay, I don't see any question. Let's now start from here. This is the point where we got last time. Let's start from here, because what is our purpose? Our purpose is precisely to compute runoff. And therefore, we have to compute the integral under the red curve. This is, in mathematical terms, what we have to do now. And keep in mind that the integral under the red curve is the cumulative contribution to runoff. So it's, or you can call it river flow. The difference between runoff and river flow is very subtle. For now, let's assume that they are synonyms. I'll explain to you later what's the difference. But you can assume they are synonyms. And therefore, again, the integral under the red curve is the cumulative runoff, cumulative river flow from the beginning of the event. Okay? So if we are interested in computing the river flow at each time t, we will have to compute the increments of this cumulative river flow in order to compute the river flow at a given time. But we will see this later. Now, so as I said, we have to compute this integral. And before we move forward, let's note that we are assuming, you can't see it here, but in my website I updated because this specification was missing, it was implicit. We are assuming that C0 is equal to 0, which means that at the beginning of the event, we have 0 rainfall, 0 cumulative rainfall. This is fine. But we also have a 0 storage in the catchment. okay, because we are making this assumption that the cumulative rainfall is equal to storage into the catchment in the unsaturated areas, and therefore let's assume that it's 0. Very good. Now we have to compute this integral, and I would like to make an experiment now, because here you can see the computation of the integral. On the other hand, there are some missing steps here. I would like, as I said, to make an experiment and to try to write on a sheet. I'm missing the blackboard because at this stage I would have written on the blackboard in a classroom. And by the way, I bought, but I'm still waiting for it to be sent to my home, a graphic table which will allow me to emulate the blackboard, but still I don't have it. So let me try to use the phone to share my blank sheet with you. I'm not sure I can succeed. Let's see. Let's see. I think I now have to look at the screen of the PC. I'm not sure I can. Let me see. Still not appearing, so just 1 second. Okay, now it should work. Just 1 second. Let's see if the connection is good enough, because I still can't see it on my screen. Doesn't appear. Just 1 second. I try again. So should be okay. Let's see if it works. Still, okay, maybe that I have to, 1 second. Okay. Let me try again. It worked yesterday, but you know, always tricky. Still can't see here. So let me see. Okay. I think I got it. 1 second. So let's see. No, still not working. Don't understand why. Okay, so I think I'll need to. You can't see a blank sheet, isn't it? I think you just see a kind of pink circle in between. Let me see if I can. Okay, let's forget about it. So let me put again the screen on the video. Okay, so sorry for that. Let's try to work on this figure. Just 1 second that I increase the size. Okay, so what you see in the first row is just the previous relationship with an integral sign on the left and right hand side. and the integral is computed between 0 and a given value of Ct. Again, remember that Ct is our rainfall from the beginning of the event. Good. Now, be also careful. I am including a variable of integration, which I indicate with the symbol key. The variable of integration is just to distinguish inside the integral the varying variable varying between 0 and Ct, which is the independent variable of my function f. Okay. Now, in the right-hand side, as I said, you just see under the sign of integral the difference 1 minus square parenthesis 1 minus key divided by Cmax to the power of beta k. Key substitutes the previous Ct variable, which is now the variable of integration. Okay, perfect. Now let's go to the second step. First of all, you see that in the first row, in the right-hand side, you have the integral of a sum, which for the additive property, which we can decompose in the sum of the integrals. So we have first the integral between 0 and Ct of 1 in the key, which is simply equal to key, okay, which is to be computed at the extremes of integration 0 and Ct. But in the second row, you get, as the first addendum, you just get key. Perfect. Now we have the integral of minus what is in the square parenthesis. So integral of minus square parenthesis 1 minus key divided by Cmax to the power of beta k. Look, there is the power of beta k, so we cannot decompose this second integral into a sum because there is the power. So we have to compute the integral of the sum between parentheses to the power of beta k. Now, this integral is precisely equal to what you see in the second row as a second addendum between the big square parentheses. So the integral is Cmax divided by beta k plus 1, which multiplies 1 minus key divided by Cmax to the power of beta k plus 1. Now, you may wonder whether this integral is indeed correct. So, in order to prove that it's correct, I suggest to use an empirical approach. Let's compute the derivative of Cmax divided beta k plus 1, which multiplies 1 minus key divided by Cmax to the power of beta k plus 1. Let's compute this derivative and let's check if it is indeed equal to the quantity which is between square parentheses above. Perfect. Now, second row, the derivative of this product, Cmax divided beta k plus 1 times square parentheses, is, first of all, the exponent, beta k plus 1, which multiplies everything, okay? And then you get the square parentheses, which is the derivative inside this parenthesis is exponent minus 1. Okay, so beta k plus 1 minus 1 is just beta k, which multiplies the square parenthesis itself unchanged. Okay, and then I have to multiply by the derivative of the quantity between square parentheses, which is minus 1 divided by Cmax. Okay, so what you obtain is precisely the fact that the multiplier beta k plus 1 that I get in the result of the derivative annihilates with the denominator of beta k plus 1. And the multiplier minus 1 divided Cmax annihilates with the numerator Cmax. And what you get then is precisely the quantity between square parentheses that you see in the first row. I'm sorry, explanation, of course, it's not really clear done by words, but if you try to compute yourself the simple derivative, indeed, you see that the integral is correct. Give me 1 second, sorry. Okay, perfect. Now what we have to do is, if we accept the fact that the second row right hand side is the correct integral of the right hand side above, we have to compute the right hand side of the second row between the extremes 0 and ct. If you substitute, what you get is the third row, which is ct. Look at the right hand side. The first addendum is ct. Why ct? Because it's key computed between ct and 0. So key, if you substitute ct in key, you get ct minus 0. So 0 goes away, and you get only ct. And then for the second addendum, you see that what you get for key equal to ct is precisely the second addendum in the last row. The second addendum in the last row is just the quantity above second addendum computed for key equals ct. Perfect. Now you have to write minus the second addendum in the right hand side second row for key equal to 0. And this is, if you substitute for key 0 in the second row, you get 1 minus 0 to the power of beta k plus 1, which is 1. So you only remain with minus Cmax divided beta k plus 1. This is precisely what you get. And again, what is this? This is the integral under the curve, f key in the key. So it's the integral under our previous red curve. It's simply the cumulative runoff from time 0 and time t. Okay, this is our cumulative runoff. Okay, good. Now let me go back to the website. So what is, if we accept that this quantity, meaning the quantity that you now see in the upper part of the screen, this quantity is, as I said, cumulative runoff from the beginning of the event. Now, if we want to compute the water volume stored in the catchment, this is simply equal to Ct minus the cumulative runoff, because Ct is total rainfall. If you subtract from total rainfall the storage, then you get, if you subtract from total rainfall the cumulative runoff, you get the storage. So if you get the quantity which is in the upper part of my screen, and you compute the difference Ct minus that quantity, you precisely get the storage. And in fact, if you look at the quantity in the upper part of my screen, it is right-hand side is Ct plus something. If you compute Ct minus Ct, then they annihilate each other, and therefore you just remain with the plus something, which is precisely what you find below, with the sign changed because I computed a difference. I computed Ct minus the quantity in the upper part of the screen, and therefore below I find Cmax divided by beta k plus 1. Look at the second row, minus, again look at the second row, minus Cmax divided beta k plus 1, which multiplies the quantity between square parentheses, which is unchanged with respect to the first row. And this is the storage. And then we can take take out the multiplier, Cmax divided by beta k plus 1, and then we obtain the simplified representation in the second row on the right. This is storage in the catchment. Cumulative storage from the beginning of the event, okay? Perfect. Remember, these quantities are cumulative runoff, cumulative storage per unit area of the catchment. In hydrology, we also call it cumulative specific storage, where specific stands for unit area. Okay, now it is useful for subsequent computations if you invert. I put it in the upper part of the screen. If you invert, let's give it some time because it has to update. I see that it's a bit slow now. Okay. So let's invert the quantity that you see in the upper part of the screen. Let's invert it in order to get an explicit representation for Ct, which you find in the second row. And again, this will be useful later. Passing from the first row to the second row is just a simple mathematical transformation. You have to extract Ct from the first row. In order to do that, you need to raise to a power the whole relationship, and the power is 1 divided beta k plus 1. And then with a simple mathematical transformation, you get the explicit value for Ct. Good. Now, it is interesting to note what you see here and this equation. What is this equation? It's the max storage. And when do you obtain the max storage? When Ct is equal to Cmax. Ct is cumulative rainfall. When you get cumulative rainfall, which equates the max storage into the catchment, where when I say max storage, I mean the maximum value of storage at each individual location. So I get the storage at each individual location and I get the max. So when rainfall equates the max storage over the catchment, meaning max individual storage at each location, the catchment is saturated, which means that even the single location that has the highest capability to store water, it's saturated because rainfall equates the highest capability in the catchment to store water, okay? So the catchment is saturated. When I put Ct equal to Cmax, the storage, it's like a sponge that cannot take any more water whatsoever. So everything that rains over a saturated catchment is completely transformed in surface runoff. keep in mind a saturated catchment is potentially dangerous because there is no attenuation of rainfall. Everything that it rains, you find it into your river because it's like raining over the roof of an house. The roof of an house is a catchment with beta infinity, beta k infinity. Everything, it has no storage, and therefore everything it rains there, it's transformed into flow. The same thing occurs over a saturated catchment, okay? It's interesting then to compute what is the overall storage, cumulative storage over the catchment when it gets to saturation. And this is easy to compute. It's given by this relationship. How it is derived, this relationship, simply, I go back, simply by getting the relationship that you see in the upper part of the screen, look at the right, and put instead of CT, Cmax. And therefore you get in between square parentheses 1 minus 1, it's 0. So between curly brackets you get just 1, and therefore your Wmax is just equal to the multiplier Cmax divided by beta k plus 1. Good. Any question? Because these are all the equations that we need to apply the model. And believe to me, it is complicated to explain by words, but it's not complicated to understand. It's just an integral. And you will see it even less complicated to apply in R. It's very simple. Okay? No questions? So, but I give you 30 seconds more while I put on the screen what I need. Okay. So, just 1 second because I had to decline a phone call. Okay, very good. Give me 1 minute because I can't see the chat anymore. I have to understand what happened. Okay, I see it. Very good. And let me move this here. Okay. So these equations that you see here, which are on the screen, which are the relationship which gives the cumulative storage, the relationship that gives CT depending on cumulative storage, CT depending on WT. This allows an easy application of the I-mode model. Remember that so far we neglected evapotranspiration. Also, now it's time to point out that what we are computing here is just runoff. What is runoff? It's the excess of infiltration at any location. So it is, we call it runoff, the excess of infiltration, which means that if you have a given location over the catchment, you assume that it rains over there, and then you have infiltration, which means that all the rain goes into the ground. When the location is saturated, then you get surface runoff, or simply runoff, which means that if you sum the runoff over the whole catchment, you get the cumulative runoff from the beginning of the event. But runoff, strictly speaking, is just what exceeds infiltration. It's not yet river flow. The runoff, to be transformed into river flow, needs to be, we say, routed, which means that we have to give to runoff the time to travel along the hill slopes and reach the river, where finally it gets converted into river flow. Runoff needs to reach the river. before we can call it river flow. And remember that so far we didn't make any difference. Okay, now let's compute then the river flow, but before than that, let's compute the cumulative runoff over the catchment. And in order to do that, let's consider these equations, which allows us to compute W and C. Okay, these are our two tools. We can compute W and C depending on the Cmax and beta K, and depending the values of these two variables. So we can compute W depending on C, or C depending on W. Okay, these two equations are our tool, but basically they are only one equation, because the second equation is derived from the first one. Okay, now at a given time step t, look here, one knows the value of Ct, which is equal to the cumulative rainfall depth from the beginning of the event at time t. We know this, it's an input data. Okay, so we can compute Wt. Perfect. It's clear, because we know Ct, we can compute Wt by using the above equations. At the time t plus 1, Ct plus 1 will be equivalent to Ct, which is cumulative rainfall at the previous time step, plus P. P is rainfall at each given time step. Okay, but when we compute Ct plus 1, we have to make sure that Cmax is not exceeded, because if we get to the value of Cmax, then C doesn't increase anymore. So we have to put a condition. I am highlighting it. Just 1 second that you get it on your screen. The condition is, we need some time, we need to give the connection some time. Okay, now you are getting it. The condition is that C plus 1 is equal to Cmax if Ct plus Pt is greater than Cmax. Good. And then we can compute a first contribution to surface runoff, which is given here. So the first contribution is given by the exceedance of Cmax if we get it. So if we exceed with rainfall Cmax, the exceedance is all transformed into surface runoff. So let's compute this expression right hand side. Maximum value between, separated by commas, between Ct plus Pt minus Cmax and 0, which means that if the max is 0, then this contribution is 0. If instead the max is greater than 0, it means that the difference Ct plus Pt minus Cmax is greater than 0, which means that Ct plus Pt exceeded Cmax. So if there is an exceedance, then ER1 is equal precisely to that exceedance. If there is no exceedance, ER1 is 0. This is a first contribution, which again we get only if the catchment gets completely saturated. And in a way, this is the kind of contribution that is active during flood flows, because, it's a saturation contribution. Now, let's compute a second contribution, which is given by the water volume, the rainfall volume that cannot be absorbed by the catchment, because the catchment in some parts it's saturated. It's not completely saturated, but it's saturated in some of its parts. And what rains over these parts, it's transformed into runoff. This second contribution can be simply computed in this way. See this relationship which I am selecting now. You need some time to get it. And it's ER2. It's called ER2. Now, maybe I hope that you can see clearly on the screen even if it's selected. It's given by a difference between two differences. It's a unique sum, actually. But it's interesting to show it as it's shown here as the difference between two differences. The first difference is CT plus 1 minus CT. This is rainfall at the given time step. So it's just hourly rainfall in our case, rainfall at each time step. This rainfall, is it transformed into runoff? Yes, no. It's only transformed into runoff the part that is not absorbed. And what is the part of rainfall that is absorbed? It's the difference, WT plus 1 minus WT, difference in storage. So I take rainfall at each time step and I remove the storage at the same time step. In this way, I get at each time step the contribution to runoff. And then I can sum year 1 plus year 2 and I get the contribution, overall contribution in the catchment to surface runoff at each time step. And this is what I wanted to compute. But still, we didn't take evapotranspiration into account and we didn't take river routing, runoff routing into account. So let's now take into account evapotranspiration, okay? Evapotranspiration, as I said, we don't discuss it in detail. It is a contribution that is extremely important for water resources management, so our interest. Actually, it is extremely important for our interest. It's not much important when you have floods because it plays a minor role. Or let's say a minor role with respect to the role it plays in dry periods. In dry periods, you know, evapotranspiration has a major impact on water resources availability. Also, when you build reservoirs, evaporation from the reservoir in the dry season is extremely important. So you may ask why you are not teaching us in detail how to compute evapotranspiration. Because, as I said, evapotranspiration is computed empirically, and it's nothing difficult. The only problem is to get the data. To get the data, because in principle you need data on solar radiation, you need data on wind, you need data on temperature, you need data on relative humidity. So it's not easy just for the data requirements. But once you have the data, it's computed through empirical relationships, which were derived by interpolating field data and experimental methods in the lab. So it's just a matter of finding on the web what is the empirical relationship that you need. So this is why I don't dedicate much time. I prefer to dedicate time to the more conceptual topics in this course. And I mean, I said it's just a matter of finding the empirical relationship that you need. And then the next question is, what is the basis for the selection, the criteria for the selection? If I have several empirical relationships, what is the basis for selecting the most appropriate one? The basis is, again, data availability. If you have any empirical relationships needs data. And they differ each other, these empirical relationships, based on data requirement. So you have to select the one that fits your data availability. That's it. And in most of the cases, you just have temperature. And you are already lucky if you have temperature. Because, you know, it's not so easy to combine rainfall data with temperature data with river flow data. It's not easy. But in most of the cases, if you succeed in getting the temperature. Now, how it is computed the evapotranspiration in general? First of all, let's divide between potential and effective evapotranspiration. Potential and effective. There is a link here that describes potential evapotranspiration. If you click, you see that there is a Wikipedia page linked. You can study what's the difference there, and it's very simple. Potential evapotranspiration is the one that you get when you have plenty of water. If you have plenty of water, your plants transpirates more because they are very happy. They try to use all the water they need, and therefore they transpire a lot. Also, if you have a lot of water into the soil, you have all the possible evaporation. This is the potential evapotranspiration when plenty of water is available. The effective evapotranspiration is what you actually get, which is lower than the potential because usually you are in dry conditions. In dry conditions, plants reduce transpiration in order to save water, and you have less evaporation from liquid water because you have less liquid water. And for instance, if you think at a situation where you have zero water in the soil and in the soil surface, zero water means zero effective evapotranspiration. So there is this important difference: potential evapotranspiration, effective evapotranspiration. Let's suppose that we know the potential evapotranspiration, and this is actually the reality because all the empirical relationships that we can consider give you an estimate of the potential evapotranspiration. Now, it's usually introduced into each model a way to compute effective evapotranspiration depending on the potential. And the relationship that you see here, let me expand it. It's precisely the relationship that is used in IMOD to compute effective evapotranspiration, ET, left-hand side, depending on potential evapotranspiration, EPT, right-hand side. And the quantity between parentheses is a reduction factor. Actually, it is a reduction factor which depends on the storage of the catchment WT. I said when there is plenty of water, it means that, of course, in the catchment you have a high storage. We expect that ET increases. So I expect that ET is increasing for increasing WT. And conversely, when WT is 0, it means no storage, it means no available water. I expect that ET is 0. If you look at this relationship and you look at the quantity between parentheses, indeed you see that if WT is equal to 0, you get between parentheses 0, which means that ET is 0. If WT is equivalent to its max value, which is, as you remember, Cmax divided beta k plus 1, then you get between the parentheses, you get at the numerator of the second addendum, you get 0, because it's difference between Cmax over beta k plus 1 minus, again, Cmax over beta k plus 1. So you get at the numerator 0, between parentheses you get 1, and then ET is equal to EPT. It's just a linear relationship, just linear, which is fine. I mean, it serves to the purpose. And now you are left with the only problem of estimating EPT. To estimate EPT, you use an empirical relationships. In our exercises, we will assume that the value of EPT is given in some way. I hope this is clear. Now we only have the problem that we have to subtract it from something. This is a water loss. Evapotranspiration is a water loss. So we need to subtract it from something. And what is the something? It's the catchment storage. It's the ideal state variable from which we have to subtract evapotranspiration. And in fact, you see here that, let me see where it's written this. Okay, we need, here it's the relationship. let's give it the time to get selected. The water storage at time t plus 1 is given by W t plus 1 is equal to Wt minus Et. It is simply subtracted. And note that we subtract the water storage, the evapotranspiration from water storage at the end of the time step. It's just a matter of choice. So we first compute ER1 and ER2, and then before passing to the next step, we subtract evapotranspiration from the resulting storage. As I said, it's just a matter of choice. You may subtract evapotranspiration at the beginning of the time step. It's just your choice. And it's part of the numerical integration approximation, as we discussed last time. Perfect. So at each time step, what we do is precisely take the previous value of CT, then we sum rainfall and get CT plus 1. By knowing CT plus 1, we can compute ER1 and ER2. ER1 and ER2. So by knowing again at each time step, we take CT from the previous time step, we sum rainfall, and then we get CT plus 1. And then we can compute ER1 and ER2, because once that we know CT plus 1 and CT, we can also compute WT plus 1 and WT. Good. So we can compute ER1 and ER2. And then we have the surface runoff, and then we compute evapotranspiration and subtract evapotranspiration from Wt plus 1. And then we go to the next time step. That's it. It is very simple. But we still have to route the surface runoff. This is the last thing. We computed surface runoff, we accounted for evapotranspiration. Now we have to route the surface runoff. Okay? How do we route it? Let's look at this figure here. Let's look at this figure here. Now, let's look at the left rectangle with the arrows, etc. This is just another schematization of iMod. It's a graphic schematization. I think it is particularly wise because it allows to get a graphical representation of both the probability distribution and the contribution to surface runoff and also storage. And the way it is obtained, I leave to you the task of understanding the way it's obtained. But I just want to tell you that the thick black lines that you see in the bottom of the left figure, so this kind of quarter of circle, let me do this. So we breathe a little bit. Let me open it in GNU. Okay, just a second. Good. Here we are. Too big. Let's see. I think this is the correct size. Okay. So, as I said, just 1 second. Let's do like this. I need the panels. Just 1 second. Okay, this is what I need, but I need to change the color. I don't like black. Okay, now it works, but second dimension, let's put, okay, good. As I said, this quarter of circle here and then now I'm trying to follow this curved. Okay, this is just the probability distribution that you were used to see with another orientation. So if you look at the vertical axis, it's now representing CT, and it was the horizontal axis before. If you look at the horizontal axis, is representing FC, but it's with an inverse representation between 0 and 1. And it is the same representation. You see that for Cmax, for the Cmax value here, you get as FC, which is 1, which is like before. And for CT equal to 0, you get FC, which is 0. So it's the same representation, okay? And this switch of the axis and the change of orientation allows us to say, to represent graphically year 1, which is given by this contribution here. And you see, this is the exceedance of Cmax. It's the value of C that exceeds Cmax. You see, C is along this axis here. And for the exceeding part after above Cmax, you get year 1. And then you get the contribution year 2, which is this one. Like it is like before, it doesn't change anything. It's the area below the curve. Okay, and then you have the storage, this one. I wanted to change the color, just 1 second. Storage, this one. It is not an immediate, it is not immediately understandable, but it is nice because it looks like a reservoir, and it looks like it is a representation that is comparable to the representation that is used in the linear reservoir. The linear reservoir is represented like a tank. In this case, it is again a tank with the bottom, which is still horizontal, one vertical wall that is still vertical, and the other vertical wall is carved. And the shape of the other vertical wall is given by the shape of the probability distribution. So I think it is indeed a smart way of presenting it. When iMod was presented in 2000, this kind of representation was used. Now, let's now look at the sum of year 1 plus year 2, which is total contribution to surface runoff. And let me get the red color now. Now this goes towards the river, okay? So here we get the surface runoff that is going towards the river. And it is, by assumption, split in 2 parts through a parameter alpha. So a third parameter is introduced. Remember, so far we introduced in our equations 2 parameters, beta k and Cmax. Now we introduce a third parameter alpha, which you can see here, alpha, which is just a weight. It splits in 2 parts, 1 minus alpha and alpha, the surface runoff. It's just split in 2 parts. If alpha is 0.5, you get the surface runoff split in 2 equal parts. If alpha is 0, you get it split only in the upper part. If alpha is 1, only in the lower part. So it's just a linear split. And then in this way, we subdivide the surface runoff in two components. Why this? Because we want to recognize that in a catchment, there are usually two different velocities runoff reaches the river. There is a high velocity, and there is a component that has a lower velocity. And typically, the higher velocity is pure surface runoff. The lower velocity is a runoff that is still considered to be superficial, but it's a little bit more taking place into the soil. It's also called hypodermic runoff, which means that it's below the skin of the catchment. Surface runoff is assumed to be above the skin, and just below the skin you have this slower component. Keep in mind that this is just a conceptual representation, just a way to be more flexible in routing surface runoff to the river. Okay, now let's look at the upper part, this one. This one goes to a cascade of 3 linear reservoirs. So the runoff goes into this first reservoir here. You have a linear parameter K called KQ. It stays for K quick runoff. KQ is the parameter of the linear reservoir. Through KQ, depending on the storage, remember how the linear reservoir works, you get the outflow from the first reservoir, which is then used as input to the second reservoir, which is again a linear one with the same constant KQ. And then you compute the output from the second reservoir, which is then transformed into the input to the third one, and finally from the third reservoir you get first contribution, okay, which is the quick contribution. Good. Now let's focus on, let's take the yellow. Let's focus on the other component. The other component, the slow component, goes directly inside a single linear reservoir, and then it's just one reservoir. So from this reservoir goes to, again, the river. And not only to the river, it goes to the closure of the river actually, because we need to get the river flow at the closure of the catchment. So that's it. And of course you may wonder why 3 reservoirs above. It's just a subjective decision. You can put only 1 if you like. You can put 5. And it has been proved that by splitting the runoff in these 2 components, one which makes use of just 1 linear reservoir, the other one which makes use of 3 linear reservoirs, it has been proved that indeed this is flexible enough to represent several different catchments. On the other hand, we introduced 2 additional parameters, Ks and Kq. So how many parameters did we introduce so far? 5. Beta K, Cmax, alpha, KQ, Ks. These are our 5 parameters. Very good. Now, the only thing that we need is to write a program. To write a program in order to apply it. And as I said, the good thing is that the complexity is continuously decreasing from theoretical explanation in words, very complex, to the explanation of the application. You see that we just need at the end of the story 2 relationships, so it's a bit simpler. And then you will see that the translation into a numerical code, it's even simpler. So this is a nice feature. I think this model is a very nice intuition because, as you will see, it's very simple to apply. It's in a way conceptually meaningful because it allows for the storage in the catchment, local storage, to change according to the catchment behaviors. And it is also very understandable and very flexible. Very flexible. It has been proved that it works well for several catchments. If you compare it with the linear reservoir, the striking differences that you see, perhaps the most striking, is the number of parameters. The linear reservoir has just one. Here we see 5 parameters. So it's indeed a striking difference. What does it mean, an increasing number of parameters? It means more flexibility. This is why parameters are introduced. They are introduced to give flexibility to a mathematical relationship. As I said, the parameters are constants. Once you decide the value of parameters, typically they are kept constant, but you can change their value in order to fit your model to the considered catchment. So they give flexibility. The higher the number of parameters, the higher the flexibility. This is a typical solution when one modeler prepares a model of whatever and the model doesn't fit the data. The typical solution is to put additional parameters to give more flexibility, because it's like when you use a function to pass through some points, and you start first with a straight line, which is the simpler function, but usually the straight line doesn't pass precisely over the points. So you introduce a first curve through a parameter, and then a curve means a curvature through a parameter, but then still you may get that some points are not fit, and therefore you introduce another additional flexibility with another curvature. So it's adding parameters allows to get flexibility. And then one may think, but why then don't we add hundreds of parameters? Because the problem is that parameters need to be estimated, and to estimate them, it is simple if you have just one. Do you remember what we did with the linear reservoir? We just made a trial and error procedure. We just changed the value of k, and it was easy to find the correct value. Now think if you have 2 parameters, it's more and more difficult because you have to explore a combination of 2 parameters by trial and error. So your number of trials increases a lot. Think of 5. 5, it's almost impossible to use a trial and error procedure because you have too many combinations to explore. So it becomes more difficult to calibrate these parameters. So this is the one drawback of one disadvantage of flexible models. And then there is another thing to say, which is extremely important. When you estimate parameters, you get their optimal value with uncertainty. And you can understand uncertainty thinking of, for instance, the linear reservoir. Let's suppose that you get the data set that I gave to you, and you find the optimal k value. Okay, and then let's think of splitting the data set in 2 parts, and for each of the 2 you want to estimate the optimal k value. You will end up with 2 different estimates, and their value will be different with respect to the first estimate that you got on the overall data set. Now, it means uncertainty. It means that depending on the data that you use, you get different values of parameters. And this is just because of uncertainty. And the more restricted the data set is, the more uncertain parameters are. You can easily check it. If you make experiments with a linear reservoir and you shorten the data set, you will see that the values of the optimal parameters will diverge. The shorter the data set, the more divergent the values will be. So the more limited the data set is, the more the uncertainty that you will get. Good. Now, uncertainty also increases for increasing number of parameters. This is something that can be easily understood. If you use more parameters, you get more uncertainty. So this is an additional drawback. It's the first drawback was more complicated calibration. Second drawback is more uncertainty. And what does it mean, uncertainty? It means that when you apply your model for simulating a hypothetical future situation, it's less reliable, which for an engineer is an important limitation. Good. Let me go back to the web page. Not this one. Not this one. I'm sorry. Okay, this one. Okay, let me go back to this web page, and basically we are 1 second because it's still changing windows, and I wait for your display. Okay, here we are. Now let's look at this web page. We got to the end of the iMod model, and also we talked a little bit about calibration. And now we are ready to the next step. The next step may be application on R of the iMod model or discussion on groundwater models. I prefer for the next hour at this stage, I would prefer to discuss the groundwater models and then to postpone the iMod application in R to Thursday. And the reason is that I don't think we may succeed in only 40 minutes to make this exercise. I think the exercise is extremely important, and then I would prefer to postpone it. And okay, now it's we still have 5 minutes to go, and I first of all would like to open to your questions. And there is first of all, I have a question for you, and my question is today I spoke more rapidly, and you know, I am not sure, meaning that the velocity with which I spoke today in a classroom would be too high, because in a classroom you have to write down, and here it's a different situation. So first of all, please let me know if I spoke too quickly, and if yes, that's fine. I will slow down for the next hour and next lectures. On the other hand, I need to continuously make experiments, so I hope you don't mind if today I tried to be more to be quicker. Okay, let's turn to your questions, and as I said, please feel free to step in with the micro. Any question? Okay, let's say I don't see any. Oh, okay. The velocity was okay for me, but I would like to suggest taking more breaks. Okay, that's fine. Thank you. And I forgot maybe that you already gave this. Yeah, at the beginning I forgot it. I'm sorry. And you are right, because I understand that attending a lecture on the screen it's not really okay. Yeah, yeah. I fully agree. I fully agree. And okay, so I would say let's do like this. And now let's break for 15 minutes, and because I need a coffee. And when we meet back, I would really appreciate if you could ask a couple of questions, and I would like with, let's say not a couple, 2 questions at least. I would like If you could use the micro, please. And now I am leaving for these 15 minutes. So if you want to discuss between you, who is asking the questions, or if you want to entertain a discussion, maybe this is the right time. You are not shy because I am leaving. I tell you that I am leaving, and also you can check when I am attending. And leaving means that I'm not exiting from the room. I'm just shutting down my camera, and I'm leaving. Let me see. Now I took the connection off. I'm shutting down my camera and my audio. The camera is already shut down. Now it's on. And so I am leaving. So please feel free to discuss. When I get back, I will tell you. And I'm not going to listen to you in a hidden mode. So I'll tell you when I get back. Let's say in 15 minutes from now. Okay. Any question before I leave? Okay, so I think I understood. So alpha is weight, and therefore, by definition, it should vary between 0 and 1. And so also it should be varying between 0 and 1 to make sure that you have mass balance, because if you took alpha 1.2, then you would increase the runoff. So it's a weight between 0 and 1. And what is the optimal value? First of all, we usually calibrate it. And so we will see how calibration is performed, but basically it's a trial and error. And we calibrate it, but in principle, it depends on the catchment. So if the catchment indeed has two flow components, one slow flow and one faster flow component, then we expect that alpha is in between 0 and 1. If it has only one flow component, because it may be a catchment with only groundwater or only surface flow, think of the roof of an house. It's only one component. So if it's only one component, we expect that it takes either value 0 or 1. And, you know, in principle, ideally, we would like that any parameter, alpha included, takes a value that is physically reasonable. So ideally, if I modeled the roof of my house, I would expect that by calibration, I get alpha close to the value that gives only surface runoff, which may be 0 or 1. It depends on how you define it. We didn't say we didn't define how alpha is applied. So we didn't say if alpha equals 0, I have only the lower reservoir. If alpha is equal 1, I have only the upper flow direction. I didn't say if 0 is equivalent to only groundwater flow or if 1 is equivalent to only groundwater flow. For now, it's generic. But if I have only one flow component, I would expect that it takes either 0 or 1. And because ideally, as I said, we would like that each parameter has a physical meaning. But actually, there is to say that there is uncertainty. There is uncertainty in the data, but also the model is uncertain. And uncertainty means that sometimes the physical meaning of parameters is lost. But actually, what I always suggest is when you calibrate a model, whatever model it is, like we did for the linear reservoir, we checked that the K value has a meaningful value in terms of closeness to the concentration time of the catchment. For iMod, I would say the same. So try to think at your catchment and try to figure out what you are expecting, basing on your experience. But experience, again, it doesn't mean that you have to be an old person. Experience means that you try to understand how a catchment works. So you look at a catchment, it's very steep. If it is very steep and rocky, you expect that you have a fast flow. So not much groundwater. If it is very flat and with a lot of grass and very deep soils, you expect a lot of groundwater. So you look at the catchment and you figure out how it works. and then figure out your expectation in terms of parameters, and then hopefully after calibration you can find a correspondence. If there is no correspondence at all, so you get a completely unexpected outcome, then you have to be careful. Careful means that try to understand what is the reason why you got a completely different outcome. And this is something that a modeler should always do, because any model is a simplification. We use models for a very technical purpose, so we should make sure that the outcome from the model is meaningful. So regarding alpha, I usually takes a value that is between 0 and 1, and for impervious catchment is closer to 1, for very permeable catchment is closer to 0. And if I had to specify an initial value, usually I said, let's take 0.5, just because it's the best compromise. Or if you look at the catchment and you get a different indication, just follow your intuition. I hope I replied to your question. Okay, another question? Okay, no questions. So I give up, but I don't want to push you, but I really would like that there is a better interaction. To better promote it, I received from one of you, from Maurus, availability for giving a presentation, delivering a presentation on virtual water. I suggest that we schedule this presentation next Thursday at the beginning of the lecture if Maurus agrees. And if you don't agree, write on the chat or write an email to me, no problem. And please, when delivering your presentation, try to keep it short, ideally between 5 and 10 minutes. Don't go beyond 10 minutes. Also, you have to get used to respect the time. And this is a message to everybody. When you will take your degree, you will have 10, 12 minutes to deliver your presentation. And it's extremely important that you meet the time, because if you don't meet the time that is given to you, it means that you are not organized, and the commission doesn't get a good opportunity, doesn't get a good opinion of you. And when you give interview, this is even more important. They usually give you a time. When I deliver talks at scientific conferences, they give me 12 minutes, and after 12 minutes, they shut the microphone down. So it's absolutely important. You need to learn how to meet the time. And you may ask me, how can I learn it? It is very simple. You have to try it. So try it alone yes, 10 minutes is the absolute maximum, Maurus. Just 10 minutes is the absolute max. If you can finish in 8, 9 is even better, but 10 is stop, okay? And you just have to try it, and keep in mind some quick, very, let's say, rules of thumb. The rule of thumb usually is that an average presentation takes 1 minute per slide. You don't have, if you rush the slide in order to let people read it, must stay on the screen for at least 30 seconds. But actually, given that you speak, you should compute, as a rule of thumb, 1 minute per slide. And of course, don't include the title slide in this count. So to Maurus, I would say, try to fit into 8, 9 slides plus the title. So 9, 10 including the title. This is a rule of thumb. Another rule of thumb is that when you try a presentation by yourself, you have to speak with loud voice, otherwise the timing is not equivalent. And in any case, even if you spoke with loud voice, it will happen that the actual presentation time is different with respect to the attempt that you make. Usually, the actual presentation time is a bit shorter with respect to speaking by yourself loud. In my case, it is like that. Usually it's shorter, and I see that the average student usually is shorter when presenting to people with respect to the tests that we make, and the shorter of about 10%, which means that usually if you plan 10 minutes, then you get 9. But you should check because this is personal. Another rule of thumb: don't put too much things into a slide, and especially text. Figures are fine, but if you put figures, I would suggest not more than 3. And the text, don't exceed a max of, I would say 10 lines are already too much. And also it depends, of course, also on the font that you use, but I suggest that, the number of words shouldn't be more than, as a rule of thumb, like 5 words, let's say 8 words per line times 6, 7 lines, so 50 words per slide. These are just rules of thumb, and it is extremely important that you try to get trained. And I'm speaking with all of you, not just Maurus, okay? So on Thursday, let's have this presentation at the start, and then students, please get prepared. I want questions at the end, and I will start with one question, but I want questions from you. Don't be shy, and we need interaction. Let's say Maurus, okay, no problem, I cannot share my screen. Are you sure? Are you students not allowed to share your screen? I have no problem. I mean, I can upload them, and but I thought that you were able to. But anyway, no problem. I send it to me, and then I can upload them. And when we have to change the slide, you tell me. Okay. Ludovica, we need to be promoted to organizzatori. Okay, I see. And do you think, Ludovica, it's possible for me to promote one of you to organizzatore? Did you experience this already? Okay, just let me know, because this is what I would prefer to do, because it's more. It's more. If I could promote the presenter as organizer, it's more interesting. I will check anyway, but if you have any suggestion, some other class have already done it. Okay, I'll check it. I'll check it how to. Yes, please, if you can check, so we can cross our opinions. Okay, very good. Now. I move forward with the groundwater models, and let me share the screen. And one more thing before I start. I took the video today as well, and keep in mind that the video, I still have the problem that I cannot record your voice, or it's very low, very, very low. So I don't think it is a big problem because you didn't speak much so far. And I always forget to turn the video off while during the break. So in order to save time, I will upload it as it is, and you will have to skip the time of the break. And if you spoke during the break between you, don't worry because it's not recorded. And if you see anything wrong with the videos, something lacking, just let me know. I just would like to save time and avoid. I know that YouTube allows to cut pieces, but I will upload the video as it is, and then I'll take some time to cut the break. So after maybe a couple of days, you will not find the break anymore, but for this, at the beginning, you will find it. Okay. Now, groundwater models. So far, we considered the surface water model. Remember the general context we are working on. We want to assess water resources availability. So the reason why we consider rainfall runoff modeling is that we want to reconstruct river flow. So sometimes it happens that through reconstructed river flows, we build what we call a synthetic flow duration curve in order to estimate, again, this is our problem, to estimate water resources availability. Very good. Now, groundwater flow. Groundwater flow is extremely important. The groundwater resources, we already pointed out that it's an extremely important resource. Let me share the screen before I move forward, because otherwise, yeah. Here it is. Okay, now it's shared. And as I said, groundwater resources are extremely important. We already said this, and they are extremely important because groundwater, especially during droughts, it's a very important resource, especially for lowlands. In the mountain regions, usually we don't rely much on groundwater. In the lowlands, it's an extremely important resource because typically in the lowlands, surface flow is reduced. Is reduced because there are withdrawals upstream, and also there is infiltration upstream. Because in the mountains, usually there's not much infiltration, but when we get into the lowlands, then there is a relevant infiltration because usually they are alluvial areas with a lot of permeability and then infiltration, which means that river flow, surface flow is depleted, and groundwater flow is promoted, let's say. And also there is another important feature, we already spoke about it. When we are entering into the dry season or we are getting a drought, of course, the most, let's say, the faster resources or the first resources that are depleted are the surface resources for a very simple reason. They have a travel time that is much shorter. It means that when you get rainfall, they react quickly. But when there is no rainfall, so rainfall stops, you get into a dry season, you don't have rainfall anymore. Which means that the surface resources get depleted very quickly because they react to rainfall and no rainfall quickly. On the other hand, groundwater resources react slowly. They are much slower, which means that they react to rainfall after some time. So once you get into the dry season, once you get into a drought, you have first surface resources that are impacted, depleted, and then you rely on groundwater. And this is why also groundwater is important. It's extremely important also for this reason. For water resources, it's a very important resource. The problem is that, as I said, we cannot easily see them, and therefore it's a bit of a problem to estimate groundwater resources availability. And we still don't have, I tell you, models that can tell us how much water is there. Models can give us indications on the time of reaction of groundwater to climate, to meteorology. So we can estimate if we get into a dry season, how long it takes to groundwater to get impacted. But actually, models are still unable to tell us how much groundwater is there. And the reason why they are unable is that we don't see the ground. We don't see what is beneath the surface, and therefore we need to characterize it by making probes, by drilling, but the soil, as I said, is very heterogeneous, so getting a full characterization, it's complicated. So it's not a problem of models limitation. Models in principle are able to describe, but they need a lot of information. So this answer to the question, how much water is there, how much water can I take, can be obtained only if there is plenty of information available. Good. We already spoke about inductive assessment of groundwater resources through monitoring wells. Now we need to talk about deductive assessment, which means that we have to use a model to reconstruct the information we require basing on meteorological information and basing on our knowledge of the soil, of the groundwater system. Okay, how can we build a groundwater model? First of all, we are again talking about a fluid mechanics problem. So the principles are the same. And what are the principles? In premise, conservation of mass and conservation of energy. These are the principles which underline Runoff models, and in fact, both the linear reservoir and I-mode, implicitly in our scheme, there is conservation of energy and conservation of mass. You may ask me, how do you see conservation of energy in I-mode? And I tell you, through the routing. The routing is based on reservoirs. Reservoirs means conservation of mass and energy. Now, the same principles must apply to groundwater models. And by imposing conservation of mass and energy, we, in fact, can describe groundwater flow. Of course, what I need is a full characterization of the system, of the geometry of the system. And so, in principle, I would need to know the geometry of each single pore and the physical properties of each single pore. Of course, this is not possible. Keep in mind also that it is a 3D problem. It's a 3D problem because the soil has properties that are variable along 3 dimensions. It's a 3D flow, meaning that the velocity component has a component in all, the velocity has components in all 3 directions of space. So the problem is extremely complicated. So we need to introduce assumption, of course. And we will do. We will introduce assumptions. So the first thing to do is to describe the assumptions. And let's start by, in order to introduce the assumption, we have to consider what are the physical properties of the system. And first, let me start, in order also to provide an example of what I mean with physical property, let me start by saying that groundwater flow is very slow. And this allows us to introduce important simplifications, because given that it's slow, we can first say that the assumption of steady flow is more supported. So if we wanted to introduce an assumption of steady flow, it's more reasonable. It's more reasonable with respect to the surface flow, because with the surface flow, it's the assumption of steady flow is for sure it's not as reliable. Okay, and then let's look then on the web page. Here there is a distinguishing, I'm selecting behavior of groundwater flow is its reduced capacity. Okay, which makes the assumption of steady flow a reasonable hypothesis. And let's also introduce the other hypothesis. And in this line here, you read something that is an anticipation of the mathematical development which follows. In steady state conditions, groundwater flow is described by the Laplace equation. And let's forget about it now, because it may be that you already know the Laplace equation, but if you don't, it's not absolutely a problem, because we will derive the Laplace equation here below. Okay, so let's introduce other assumptions. And the assumption are, you don't see them here because I just edited the web page on the website, and this is the mirror, so the mirror will be updated tomorrow. And there are other assumptions that in this version of the web page, the old one, were implicit. I wanted to introduce them explicitly. Another assumption is that the vertical component of the velocity vector is negligible, which means that velocity is horizontal in the groundwater flow. This is another simplifying assumption, which again it's explicitly stated in my website. So vertical component of groundwater flow is negligible. Also, we assume that the changes along the vertical of the velocity vector are negligible, which means that along the vertical, the velocity vector is unchanged. And let's assume that the motion is planar, which means that if I take a plane, if I cut the flow with a plane that is orthogonal to the velocity vector at a given point, so I take a given point in the underground and I take the velocity vector of the flow, and then I cut the soil with a plane that is orthogonal to this velocity vector. Across this plane, the velocity vector is orthogonal everywhere, which means that the motion is planar. So it's these orthogonal planes are moving parallel each other. Okay, so planar motion. This is another assumption, which implies that the groundwater flow is like a current. What is a current? Into a current, you have several fluid particles, and if you take the velocity vectors for each individual one of these fluid particles, they describe individual trajectories. These trajectories have significantly the same direction. They are at each time the velocity vector for each fluid particle are parallel each other, almost parallel each other, same direction. Which means that once that you describe the trajectory of a fluid particle, you already know the trajectory of the other fluid particles. They have more or less the same direction. So you have no velocity vectors that are diverging, converging. They are, for each fluid particle, more or less along the same direction. It is a strong simplification. And in these conditions, keep in mind that it's not written here, but it is written in the web page on my website. In this condition, for currents, you have an important property that applies, and let me write it in GIMP. 1 second. I have to write it. Yeah, here it is. Let me write it here because I want to make it clear. Okay, but it's red. Be patient, and the reason why I don't like it red. Just 1 second, and let me change this. Yeah, okay. Now should be the new one. Okay, this is white, and let me take text, and let's take it quite big. Okay, let me see if it works. It's yellow, I don't like it again. So, okay, and then let me put it 100. Good. Okay, now I think you can see it, but let me put it even bigger, 150. This is a simple relationship that I have to write. Okay, so for a current, the following relationship apply. So let's suppose that you cut your groundwater flow with a plane, therefore obtaining a cross section of this groundwater flow, like you get a cross section of a river if you cut your flow with a plane that is perpendicular to the velocity vector. Okay, so if we indicate the groundwater flow with the symbol QT, this can be expressed as the product of the velocity, the module of the velocity vector, and let's say this is an average velocity, Wm. One second, I'll put it later. And velocity vector times area of the cross section of the groundwater flow. And now let me write here m. It's still okay, good. And let me put the m here as a subscript. Just 1 second, I need to, okay. Okay, this is the relationship which applies. So once that we cut the groundwater flow with a plane, we obtain a cross section which has an area AT, and this area is in principle and in general is time changing. It's time changing because the thickness of the current, the thickness of the flow can change. So let's assume that area depends on time. If I multiply the area of the cross section times the average velocity of the flow in this cross section, then we get the amount of the flow. This applies to, just 1 second, I write here, applies to currents. Okay, this relationship applies to currents. And in order to be able to say that the groundwater flow is a current, I needed to introduce the assumption that the velocity vector is running along the same direction for all fluid particles. Good. So let's keep this relationship into account because it is important, because actually you will see that our groundwater flow equation, which we are going to derive, gives us the velocity of the flow. And the velocity, we need to know that it's equivalent, once that we know the velocity, it's equivalent to knowing the flow. And we just need to know the area of the flow, of the cross flow section, and then knowledge of the velocity is equivalent to knowledge of the flow. Very good. So this is another assumption that we introduced, planar motion. Okay, and again, the list of the assumption will be described, it's described already in the other version of the website. Very good. And then we assume that the fluid is incompressible, and we assume that for a given control volume, what is a control volume? Is a volume of ground where we apply conservation of mass and conservation of energy. So each conservation equation is applied to a volume. And in the river, it is easy to identify the control volume. You take a river, and the wet area of the river is the control volume. In a groundwater aquifer, you have to specify the geometry, which may be the whole aquifer, the whole groundwater body, or a section of it. Okay, and we assume that within this control volume there are no sources, there are no source terms, which in a more, let's say, hydraulic way can be stated by saying that there are no sources of water mass in the control volume. Okay, good. Now we are ready to start, and I want to take the suggestion by Maurus and keep 3 minutes break now. And if you have any question, you can use this time to ask questions. And let me take the chat in front of me. Okay. So here you can see on the screen now the combination of the web page, now the figure disappeared, with the figure that you can find here below. And I think that it is useful if I put the figure close to the math development here. And the way is, sorry, is this one. And I will need to move the figure just up and down in order to not cover the text. But so let me put it down now. And this figure shows our control volume. Our control volume is a portion of ground with a cubic shape because it's easier to define. In principle, the control volume can have any shape, provided if it has any shape, it's important that you describe it in infinitesimal terms. Because why is that? In any case, it needs to have infinitesimal size. Why is that? Because we need to assume that inside the control volume we have constant properties of soils and constant properties of flow, which otherwise, if we don't take this assumption, we need to assume that average conditions apply. We don't want to apply average conditions. We want to be detailed. And therefore, in order to be detailed, let's assume that our control volume has infinitesimal size. You see that the dimensions are indicated as dx, dy, dz, and the d stays for just very small, infinitesimal. And okay, let's assume that it has cubic shape. It is convenient because we can work on the 3 direction of the axis. So we have 2 horizontal direction, the x, the y, and 1 vertical direction. Okay, and so this is our control volume, and sorry, here I am. Let us denote with W, which depends on x, y, z, and time. Keep in mind that our independent variable include time. So we have 3 spatial independent variable, x, y, z, and we have also a 4th independent variable, which is time. And so we denote with W the water storage in the control volume. We denote with the symbol Q in and the Q out the inflow, total inflow and total outflow from in and from this elementary volume. Okay, and also inflow and outflow depend on time and the 3 spatial coordinates. Very good. Now let's write the continuity equation. The continuity equation is the mass balance equation. It is very simple to write it down because we can just simply say that change in storage, let me put it here, change in storage is equal to inflow minus outflow. So for our elementary volume, for our control volume, change in storage W is equal to inflow minus outflow, and the change in storage with respect to time. Okay, So the change in storage divided by the time, so the partial derivative of storage with respect to time is equal to inflow minus outflow. Very good. Now we need to provide a representation for these variables Q in and Q out. And so let's subdivide Q in as well as Q out into three components along the three axes of inflow and outflow. So the volume per unit time into phase X is equal to the flow along X, QX, flow along X, QX, times the area X, so the area of the control volume projected perpendicularly to the x-axis. So AX can be, this one, can be written as the product of dy dz. And then we obtain that the volume per unit time into phase X is QX, XYZ time times the y dz. Similar expression applies for the phase Y. The volume is QY, XYZ time times the x dz. A similar expression applies for the volume per unit time into phase Z. Okay. And therefore, the total inflow per unit time may be written in this form. So the sum of the three flow components, which is something that we can substitute in this above equation that you see on the top of the screen. Good. Now we have to write Q out. Q out can be written according to this equation, and it is equal to, again, the sum along the three components. Let's focus on the component along X, which is the first one, and it's given by QX, so inflow, plus the change of QS along the same direction X. So you have the inflow plus the derivative of inflow with respect to X multiplied the X. Okay, and then this is the flow to get Q out, flow volume out. We need to multiply times the area of each phase. I hope it's clear. Okay, no questions so far. Very good, and therefore I can substitute. And if I substitute where? Sorry, I substitute in this equation here. I substitute here Q in and Q out. Very good. Now what I obtain is what is reported in the next image here. It looks complicated, but actually it's only long because it's only a substitution. So there is a derivative of W with respect to time in the left-hand side, and the right-hand side is inflow minus outflow. You see that it's inflow, it's the first row, QX, QY, QZ, minus outflow. And the outflow has, again, three addendums, which I need to subtract. And therefore, if you make the computation, it reduces the right-hand side to the last row. There are terms that annihilate each other, so you get only the last row. Okay? And in particular, 1 second. Let me get it here. No, and I think I have a GIMP open. Yeah, it's there. Just 1 second, because I want to give you, okay, this is okay, this is our equation, and the terms that annihilate each other are these. 1 second. Okay, let me put it in red. Okay, so there is this one. I need the brush. Okay, this one, don't understand why. Ah, yeah, I see. Give me 1 second. Ah, okay, good. So this one, which compensate with this one with this one, and the third QZ with this one. So you see that you get only, at the end of the story, you get only these terms to survive. This, this, and this. Let's wait for a second that everything appears on the screen. Which you find in the last row. 1 second, I notice now that there is something missing here, and I tell you what is missing here. If I change the color, I need to correct this. Let me take a note, groundwater equation. And it is useful if I do it in the, just 1 second, on the screen, because I spot the mistakes. So it's blue now. Yes, I tell you where is the mistake here. There is only the x. Actually, here there should be the x, the y, the x, the y. Yes, because it is here. The dy is here, but it's not here. Here it's missing. Just 1 second, because it's late. It's a little bit late. Okay, now it's appearing. So the dy is missing there. Where there is the blue arrow, the last one, is missing a dy. Okay, let me take a note. Missing a dy. Missing a dy. Okay, good. Now let me go back to the web page. Okay, so we get to this final equation, which is correct, by the way. It's just missing a dy there. And it's an equation which, if you look at it, this defines a relationship between storage, W, left-hand side, and the derivative of the flow in the 3 directions. Good. Now, let's introduce a quantity which is called volumetric specific storage. And we identify it with the symbol SS. Now it's selected. What is the volumetric specific storage? Simply called specific storage. It is defined as the volume of water that an aquifer releases from storage per volume of aquifer and per unit decline in hydraulic head, which I indicate with the symbol H. So again, what is the specific storage? I have an aquifer. with a given volume and a given hydraulic head. I will explain to you in a moment what hydraulic head is. If I impose a unit decline in hydraulic head, then I get a volume of water from this aquifer. The volume of water that is released by the aquifer per volume of aquifer and per unit decline in hydraulic head is the specific storage. Okay, so what is the hydraulic head? So what is this quantity, which if I decrease it, I take some water? So first of all, imagine that you have an aquifer and through, and let's suppose that it's unconfined. You know what is an unconfined aquifer, okay? It means that the surface of the aquifer is in direct contact with the atmosphere into the soil. Okay, let's suppose that through a well you take some water and then you have the level of water in the aquifer which goes down. Okay, and the level of water that goes down, the level of water is the hydraulic head. It's an indicator of energy of the aquifer. And why it's an indicator of energy? Because it's an indicator, the level of an aquifer, it's an indicator of potential energy. So the hydraulic head is precisely the energy of the aquifer, which can be given that the velocity, so the kinetic component of energy is negligible. The level of the aquifer is an indicator of its energy. So if you impose a decrease in the hydraulic head, it means that you are taking some water. And you may ask me, what is the equivalent of hydraulic head for a confined aquifer? Because the level doesn't change if I take some water, it's confined. Well, if you dig a well into a confined aquifer, if you dig a well, then you have a water level into the well, which is whatever it is. So again, if you take some water from the well, then you have a decrease of the level of water into the well, which is again the hydraulic head. So whatever it is, whatever the aquifer is confined or not confined, if you dig a well, then you get a level into the well, which is the hydraulic head of the aquifer. Okay, again, it's corresponding to the energy. Good. Very good. And remember, energy of a body is proportional to its mass. So this is why when I take some water from an aquifer, I decrease the energy of the aquifer because I'm taking out mass. Okay. Very good. So now we understand what is the volumetric specific storage. So we take some water from an aquifer, we have a decrease in hydraulic head. The volume of water taken from the aquifer per unit volume of the aquifer, unit decline in hydraulic head is the specific storage. Perfect. So we can express the specific storage. I know that I'm taking some more time. Apologies, I'm closing the lecture soon. So I can express now the change in storage into the aquifer, W, derivative of W with respect to T, has the product of specific storage times the volume of the aquifer. Good. Now, specific storage times the change of the head. So at the right-hand side, you have specific storage multiplied by changes of the head in time and the volume of the aquifer, and then you get the change in volume. Very good. I think it is clear. And then I can combine the two equations. The two equations, namely this one here and the one that I just obtained. Okay, this now you have it on the screen. I can combine this one with the one that I just obtained here. You see that W is the same left-hand side, so I can combine the two right-hand sides. And then I obtain this one. Okay, And you see that in this equation, in each term is multiplied by the x, the y, the z. So I can just divide each term by the elementary volume, which is the product, the x, the y, the z. And then I get this one. Which can be expressed in compact terms through the operator divergence. And then I obtain finally what I wanted to take. This is the groundwater flow equation. What you just have to remember is definition of specific storage here. Now I am stopping here, and just keep in mind that this is a partial differential equation, and therefore in order to obtain an explicit representation for the flow, which is what we need, it is what we need, because flow is equivalent to water withdrawal, so I need to get an explicit representation for flow, I need to integrate this equation. Okay, students, any question? Let me show you my face. Now you should see it. I will upload the video just now, and remember on Thursday morning Maurus will deliver the presentation on virtual water, and then we will move forward with iMode application in R. Okay, I wait 1 more minute for you if you wanna ask any question. Now I have also a question. Yeah, please, please. No, it's a general presentation. I don't want to give any limitation to your creativity. Of course, it has to be related to what we are studying and not what I am teaching, because it should be some more with respect to what I am teaching. And then if it's referred to your country is fine, but because I think everyone is interested in knowing what are the problems your country is facing, but it's not necessary, absolutely not necessary. Like, for instance, the first proposal that I got by Maurus is virtual water trade, which means I don't think it is specifically referred to his country. We will see, but it is not necessary. Yeah, no problem. Yeah. Sorry, say again. For I'm sorry. Ah, you mean yes, it's possible. You can work together, yes. But ideally, if you work together, I would like to listen from both of you, because it's interesting also to see your capability to deliver a presentation, your ability, and therefore it would be interesting if you could split your time. And split your time, you can take some more if it is, I mean, the max for Maurus is 10 minutes. If you are 2 persons, okay, you can take 12, okay? Is it clear? Okay, but I would like to plan one presentation, no more than one per each lecture. So on Thursday, we will go with the first one by Maurus. And then when you are ready to deliver your presentation, just let me know. And I may ask you to wait a little bit, okay? this is fine. So we could schedule, if you confirm to me on Thursday, we can schedule for next Monday. Okay, perfect. No problem. Thanks to you all. And now I think we can close. As usual, if you have any question, write on the chat. I wanted to tell you one thing because I am trying to exchange best practices with my colleagues in order to find a way to find ideas for being proactive and exciting in these remote lectures. If you have any suggestion for me, like look, there is another professor who is using I don't know what, just let me know because I'm just looking for suggestions and I don't mind getting criticism. Okay. Thank you, students, and let's meet on Thursday, 9:15. Thanks a lot. Ciao.